Whenever we look up at the night sky, our eyes are naturally drawn to the light. We see the brilliant, steady glow of planets in our own solar system. We see the twinkling diamonds of distant stars scattered across the dark canvas of space. If the night is clear, and we are far enough away from the glow of city lights, we might even see the faint milky band of our own galaxy spreading out like a luminous river across the heavens. We are creatures of light, and so we look for it. We map the universe by its glowing beacons. We define the cosmos by the things that shine. But the truth of the universe is much quieter and far more vast than the scattered islands of starlight would have us believe. The overwhelming majority of the cosmos is not made of stars or planets or glowing clouds of gas. The overwhelming majority of the universe is made of empty space. It is a profound, echoing darkness. It is the silence between the notes of a song. For a very long time, human beings thought of the space between the stars as simply a void. We believed it was a profound emptiness, a stage upon which the drama of the cosmos was played out, but possessing no substance of its own. We looked at the galaxies, those majestic pinwheels of light containing billions of stars, and we saw them as isolated cities in an infinite empty wilderness. We call this wilderness the intergalactic medium. It is the space between the galaxies, and as our understanding of the universe has deepened, we have slowly come to realize that this space is not entirely empty. It is not a perfect vacuum. It holds its own secrets, its own subtle materials, and its own faint whispered stories. But because it is so incredibly dark and so incredibly vast, listening to those stories has been one of the greatest challenges in the history of science. To hear a whisper across an ocean of darkness, you need an instrument of unimaginable sensitivity. You need an eye that can see the faintest traces of warmth in a freezing void. You need the James Webb Space Telescope. Floating gently in the quiet darkness of space, about 1 million miles away from Earth, the James Webb Space Telescope is the most complex and delicate eye ever opened to the cosmos. It does not orbit our planet. Instead, it orbits the Sun, resting in a gravitationally stable region known as Lagrange Point 2. Here, it can turn its back on the overwhelming light and heat of the Sun, the Earth, and the Moon. It is a solitary sentinel, suspended in the deep freeze of space. To protect its sensitive instruments from even the slightest hint of warmth, it deploys a massive sunshield, the size of a tennis court, made of 5 gossamer-thin layers of a specialized material called kapton. This shield reflects the heat of our solar system away, allowing the telescope's mirrors and sensors to plunge to temperatures hundreds of degrees below zero. In this profound cold, the telescope achieves a state of perfect stillness, ready to listen to the oldest and faintest light in the universe. The telescope itself is a beautiful structure. Its primary mirror is a wide, shallow bowl made of 18 hexagonal segments. These segments are crafted from beryllium, a lightweight and incredibly strong metal, and they are coated in a microscopic layer of pure gold. Gold is used not for its beauty, though it is undeniably beautiful, but for its unique physical properties. Gold is a perfect reflector of infrared light. Infrared light is the key to unlocking the deepest secrets of the cosmos, and especially the secrets of the dark spaces between the galaxies. To understand why, we must think about the nature of the universe itself. The universe is not static, it is expanding. Every day, the fabric of space is stretching, growing larger, carrying the galaxies further and further apart from one another. Imagine drawing dots on a balloon and then slowly inflating it. The dots do not move across the surface of the balloon, but the space between them stretches, and so they recede from each other. This is how the universe expands. And this expansion has a profound effect on light. When a distant object emits a ray of light, that light begins a long journey across the cosmos. If the journey takes billions of years, the very space through which the light is traveling is stretching. As the space stretches, the light wave stretches with it. Its wavelength becomes longer. In the spectrum of light, longer wavelengths correspond to the red end of the rainbow. This phenomenon is known as cosmological redshift. If a wave of light travels for a long enough time across the expanding universe, it is stretched so much that it shifts entirely out of the visible spectrum. It becomes infrared light. Our human eyes cannot see infrared light. We feel it as heat, like the warmth radiating from a gentle fire, but it remains invisible to us. The ancient universe and the vast distances of intergalactic space are awash in this invisible glow. The James Webb Space Telescope was built specifically to capture this stretched, exhausted light. It is designed to see the invisible. When it turns its golden gaze toward the dark patches of the sky, it is not looking for the bright, energetic light of nearby stars. It is gathering the long, slow, red waves that have traveled across the silent voids for millions or even billions of years. It takes patience to look into the darkness. When astronomers use the Webb telescope to study the intergalactic medium, they must point the mirrors at a seemingly empty patch of sky and wait. They hold the telescope perfectly still, letting the great golden eye soak in whatever stray photons might be wandering through the void. It is a process of deep, meditative accumulation. A single particle of light, a photon, might have originated billions of years ago. It might have been born in the heart of an ancient star or generated by the slow cooling of gas in the early universe. Once free, it begins its silent journey. It travels through the unfathomable emptiness between the galaxies. It passes through vast clouds of dark matter. It avoids the gravitational pull of black holes. It simply moves forward at the absolute speed limit of the universe, while the space around it expands and stretches its form. After an eternity of travel, this single, tired photon reaches our solar system. It drifts past the orbit of Mars. It approaches the Earth. And then, in a moment of extraordinary alignment, it strikes the golden surface of one of the James Webb Space Telescope's hexagonal mirrors. The photon reflects off the gold, bouncing gently toward the secondary mirror suspended in front of the primary dish. From there, it is directed down into the heart of the telescope, into a suite of incredibly sensitive detectors that are kept artificially colder than the surrounding space. The photon strikes the detector, registering as a tiny, almost imperceptible blip of electrical energy. One photon is a ghost. It means almost nothing. But over hours and days of silent observation, millions of these ancient, stretched photons arrive. They gather. They accumulate. Slowly, out of the darkness, a picture begins to emerge. A signal is formed. When we hear the word signal, our minds often leap to the dramatic. We imagine rhythmic pulses of radio waves or a mathematical pattern sent by some distant, intelligent civilization trying to reach out across the void. In the quiet, meticulous world of astronomy, a signal is usually something much more fundamental, though no less profound. A signal is simply information carried by light. It is a spike in a spectrum. It is a faint glow where there should be darkness. It is a signature of elements, of temperature, of motion, written in the language of physics. Recently, the James Webb Space Telescope focused its golden mirrors on a deep, dark region of the cosmos. It bypassed the glowing arms of spiral galaxies. It looked past the dense, chaotic clusters where thousands of galaxies swarm together like bees. It looked into the spaces in between. It looked into the intergalactic void. The expectation, based on generations of astronomical observation, was that this space would be incredibly quiet. Perhaps there would be the faintest, almost undetectable signature of extremely diffuse hydrogen gas, a remnant of the Big Bang itself, floating like a fine mist in the darkness. But the void is never entirely empty, and the universe is never completely silent. As the hours passed and the infrared photons slowly gathered on Webb's detectors, a signal began to form. It was not a roar of energy. It was a whisper. But it was a clear, distinct whisper coming from a place where there should have been only the quietest static. The golden eye of the telescope had detected an anomaly. In the deep, freezing expanse of intergalactic space, untethered to any galaxy, unbound by the gravity of any known star cluster, something was emitting a faint, steady light. It is in these moments of unexpected discovery that the true beauty of science is revealed. The universe is not a closed book. It is a vast, unfolding mystery, and every time we build a better tool to look at it, it shows us something we did not anticipate. The detection of this signal from the lonely dark prompts a profound shift in our perspective. It forces us to ask what it means to exist in the spaces between the worlds. To truly understand the nature of this signal, we must first immerse ourselves in the environment from which it came. Try to imagine the sheer scale of intergalactic space. It is a difficult concept for the human mind to hold. Our brains evolved to understand distances we can walk, or rivers we can cross, or perhaps the distance to the horizon. We struggle to comprehend the distance to the moon, let alone the distance to the nearest star. Intergalactic space operates on a scale that renders even stellar distances insignificant. If we were to shrink our entire Milky Way galaxy, with its hundreds of billions of stars, its sprawling spiral arms, and its massive central black hole, down to the size of a standard dinner plate, the nearest major galaxy, Andromeda, would be another dinner plate sitting about 20 feet away. Between those two plates lies the intergalactic medium. It is an ocean of almost unimaginable emptiness. If you were to take a cubic meter of the air we breathe on Earth, it would contain billions upon billions of molecules, constantly bouncing off one another. If you were to take a cubic meter of space from the void between the Milky Way and Andromeda, you might find, on average, a single atom. One lonely proton drifting endlessly in the dark. This is the environment of the void. It is a place of profound cold, hovering just a few degrees above absolute zero. It is a place of perpetual night, where the nearest stars are so impossibly far away that they do not even register as faint points of light, but are completely lost to the darkness. It is a place where gravity, the great sculptor of the universe, has loosened its grip. The gravitational pull of the distant galaxies is nothing more than a gentle suggestion, a subtle curve in the fabric of space-time. And yet, it is precisely from this environment that the James Webb Space Telescope gathered its delicate harvest of infrared light. The signal was faint, a mere murmur against the backdrop of cosmic silence, but it carried a specific signature. In astronomy, we do not just look at the brightness of a light, we look at its spectrum. Imagine passing a beam of white sunlight through a glass prism. The prism bends the light, spreading it out into a rainbow of colors. This is a continuous spectrum. But if you look closely at the spectrum of a star, you will see thin, dark lines crossing the rainbow. These are absorption lines. They are created when the cooler gas in the outer atmosphere of the star absorbs specific wavelengths of light. Different chemical elements absorb different, precise wavelengths. By reading these dark lines like a cosmic barcode, astronomers can determine exactly what a star is made of. Conversely, if a cloud of gas is heated, it will emit light at those exact same specific wavelengths, creating bright lines against a dark background. This is an emission spectrum. When the scientists analyzed the faint light gathered by Webb from the intergalactic space, they passed it through the telescope's incredibly precise spectrometers. They looked for the barcodes. They were searching for the fingerprint of whatever was glowing out there in the lonely dark. The data trickled down from the Lagrange point, a stream of digital ones and zeros transmitted across 1,000,000 miles of empty space to the giant radio dishes on Earth. As the computers translated this data into a visual spectrum, the nature of the whisper began to reveal itself. It was not the smooth, continuous glow of a perfectly black body, like a piece of cooling iron. Nor was it the chaotic, mixed signal of a distant, unresolved background galaxy. The spectrum showed distinct characteristics. It showed the signs of matter, of structure, of a physical source radiating energy into the cold. One of the most profound realizations that comes from studying the intergalactic medium is that it is not a pristine, untouched wilderness. The universe is a dynamic, sometimes violent place. Galaxies are not static objects. They are swirling, churning ecosystems of gas, dust, and stars. And over the billions of years of cosmic history, galaxies interact. They brush past one another. Sometimes, they collide. When two massive galaxies collide, it is a slow, majestic process that can take hundreds of millions of years. The stars within the galaxies rarely hit each other because the space between stars is so vast. But the gravitational forces unleashed during a galactic merger are immense. Long, sweeping tails of stars and gas, called tidal tails, are ripped from the main bodies of the galaxies and flung out into the surrounding space. Through these majestic interactions, and through the explosive power of supernovae that can blast stellar material out of a galaxy's gravitational well, the intergalactic medium has been seeded with heavier elements. It is lightly dusted with carbon, oxygen and iron, the ash of ancient stars floating in the void. So, when a signal is detected from this deep space, the first question astronomers ask is, what is the source? Are we seeing the faint glow of this incredibly diffuse gas, somehow heated by the distant radiation of galaxies? Or are we seeing something more defined? The clarity and specific characteristics of the signal caught by the Webb telescope suggested something more concentrated than a thin, wandering mist of gas. The infrared glow had a profile that matched the thermal emission of something small, localized, and surprisingly warm, compared to the surrounding deep freeze. It is here that the imagination begins to wander into the profound and the melancholic. If the signal is localized, it means there is an object out there, an entity existing entirely alone. Consider the possibility of an intracluster star. We are accustomed to thinking of stars as residents of galaxies, bound by gravity to a swirling metropolis of light. Our own sun orbits the center of the Milky Way, accompanied by billions of neighbors. But the universe can be a harsh place. During the chaotic gravitational dances of galactic collisions, some stars are thrown off course. They gain too much velocity, they reach escape velocity. These stars are violently ejected from their home galaxies. They cross the invisible boundary of their galactic halo and continue outward, moving fast enough to escape the gravitational pull entirely. They become rogue stars, intergalactic wanderers. Imagine the sky from a planet orbiting such a star. If a solar system were to survive the violent ejection, and it is physically possible that planets could cling to their star during the eviction, the view from those worlds would slowly, over millions of years, change. The bright starry sky of their home galaxy would gradually recede. It would shrink from a wraparound canopy of light into a dense, bright smudge in the distance. As the star traveled further and further into the void, the sky would grow profoundly dark. Eventually, the night sky would be completely black, devoid of any visible stars. The only light would come from their own sun. They would be an island of warmth and light drifting through an endless, freezing ocean. Such rogue stars must exist. The physics of galactic interactions guarantees it. And while they are incredibly difficult to see because they are just single points of light isolated in the dark, the James Webb Space Telescope is precisely the kind of instrument that could catch their faint, lonely glow. A wandering red dwarf, burning slowly and steadily in the absolute silence of the intergalactic medium, would emit exactly the kind of faint, stretched infrared signal that Webb is designed to capture. But the signal in the data held layers of complexity. While a rogue star was a poetic and plausible explanation, the specific shape of the spectrum, the balance of the wavelengths, hinted that the source might not be burning with the nuclear fusion of a star. It was fainter. It was cooler. If it was not a star, what else could drift alone in the vastness between the galaxies? The universe is generous in its creation of objects. For every star that ignites, casting light into the cosmos, there are countless smaller, darker bodies that form in the dusty disks around them. Planets, asteroids, comets. Our own solar system is littered with the debris of its formation. Just as stars can be ejected from galaxies, planets can be ejected from their solar systems. In the chaotic early days of a planetary system, when giant planets are migrating and gravitational tugs of war are common, smaller worlds can be slingshotted out of their orbits. They are cast away from the warmth of their sun, sent tumbling into the interstellar space of their galaxy. We call these rogue planets. They drift in the dark, freezing over, preserving whatever internal heat they might have in a thick crust of ice. Now, take that process one step further. Imagine a rogue planet that is not just wandering within a galaxy, but one that existed in a galaxy that was subsequently torn apart by a collision. Or imagine a rogue planet that happened to be near the edge of a galaxy when a passing massive object stripped it away. It is entirely possible that the intergalactic void is populated by trillions of orphaned worlds, planets without stars, worlds locked in perpetual midnight wandering through the ultimate emptiness. Because they have no star to warm them, these intergalactic rogue planets would be incredibly cold. They would be dark objects, but they would not be perfectly at absolute zero. If they were large enough, perhaps the size of Jupiter or larger, they would still retain the heat of their own formation deep within their cores. They would slowly radiate this internal heat out into the void. This thermal radiation, escaping from a dark, isolated world drifting between the galaxies, would be incredibly faint. It would be a weak, long-wavelength infrared glow. To any telescope built before the James Webb, such an object would be completely invisible. It would be a ghost ship in the cosmic ocean. But Webb's golden mirrors are sensitive enough to feel the warmth of a bumblebee at the distance of the moon. Looking into the deep void, Webb gathered the photons, compiled the spectrum, and presented a whisper of warmth that perfectly matched the profile of a massive, cooling, solitary object. As astronomers scrutinized the signal, adjusting their models and carefully subtracting any possible background noise, the reality of the observations settled in. They were not looking at a distant galaxy. They were not looking at an instrumental error. They were looking at a solitary traveler in the darkest, quietest place in the known universe. The realization brings a sense of quiet awe. We spend so much time trying to understand the bright, chaotic, noisy parts of the cosmos. We study the explosions, the collisions, the furious churning of gas and radiation. But the universe also possesses a profound stillness. The signal from the intergalactic space is a reminder that even in the vast nothingness there is presence. There are objects living out silent, incredibly long histories far removed from the turbulent life of the galaxies. The light from this lonely object traveled for an unimaginable length of time, crossing a void that is almost entirely empty, stretching and cooling as the universe expanded around it, until it finally came to rest against a golden mirror built by curious creatures on a small blue planet. This is the nature of cosmic exploration. It is not always about finding grand, fiery spectacles. Sometimes it is about listening closely enough to the silence to hear a single, isolated note playing in the dark. It is about acknowledging the quiet, hidden corners of reality and recognizing that even in the deepest, most absolute isolation, the universe continues to hold form and mass and the faint, persistent memory of warmth. To truly grasp the magnitude of a signal emerging from the spaces between galaxies, we must first change how we visualize the universe itself. When we picture the cosmos, we often imagine a vast, empty room painted black, with galaxies scattered randomly across it like glowing dust motes. But the reality of the universe is far more structured and far more deeply interconnected than this simple picture suggests. The universe has an architecture. It has a skeleton. This skeleton is known as the cosmic web. It is the grandest structure in existence. If we could somehow step outside the universe and look at it as a whole, we would not see a random scattering of light. We would see a magnificent luminous sponge. We would see colossal filaments of matter stretching across billions of light years, weaving and intersecting in a complex, three-dimensional tapestry. These filaments are the highways of the cosmos. They are composed primarily of dark matter, a mysterious and invisible substance that makes up the vast majority of all mass in the universe. We cannot see dark matter directly. It does not emit light, it does not reflect light, and it does not block light. It is entirely transparent. But we know it is there because of its gravity. The gravity of dark matter shapes the universe. It is the unseen riverbed that guides the flow of the visible cosmos. Galaxies, with all their brilliant stars and swirling gas, do not simply float aimlessly. They are drawn to the densest regions of this dark matter web. They form and grow at the intersections where the great filaments cross. These intersections are the bustling metropolises of the universe, incredibly dense clusters where thousands of galaxies are bound together in a gravitational embrace. But what about the spaces in between? What about the vast dark regions bounded by these glowing filaments? These are the cosmic voids. The voids are the great deserts of the universe. They are regions of space that are almost entirely devoid of galaxies, of stars, and even of the invisible dark matter. They are bubbles of emptiness, millions of light years across, expanding ever outward as the universe grows. To travel through a cosmic void is to experience the most profound isolation imaginable. Yet, even in the deepest heart of a void, there is no such thing as absolute emptiness. The boundaries between the luminous filaments and the dark voids are not sharp, they are gradual. The intergalactic medium, that incredibly thin mist of hydrogen and helium atoms, drifts through these spaces. And occasionally something else drifts through them too. Imagine the journey of the object that the James Webb Space Telescope has detected. Let us assume for a moment that it is a rogue planet. A massive, wandering world cast out from its home galaxy millions or perhaps billions of years ago. Its journey began in chaos. Perhaps it was born in the turbulent outer spiral arm of a galaxy much like our own Milky Way. It formed in a swirling disk of dust and gas surrounding a young star. For a time, it knew the warmth of a sun. It had a stable orbit, a predictable year, a rhythm of day and night. But galaxies are crowded, dynamic places. Stars pass close to one another, their gravitational fields reaching out like invisible hands. A near miss by a massive passing star, or the chaotic gravitational dance of a multi-star system, can disrupt the delicate balance of a planetary orbit. In a celestial game of billiards, our massive planet was struck by an overwhelming gravitational force. It was pulled away from its sun. Its orbit stretched, became elliptical, and finally broke altogether. It was flung outward, accelerating through the interstellar space of its galaxy, passing through clouds of glowing gas and past fields of ancient stars. It moved too fast for the galaxy's collective gravity to hold it back. It crossed the galactic halo, the diffuse outer shell of the galaxy, and crossed the threshold into the intergalactic void. Once it left the galaxy, its environment changed profoundly. The bright starry sky it once knew slowly faded. The light of its parent star became indistinguishable from a billion others, and then the entire galaxy shrank into a hazy, glowing patch of light in the infinite blackness. As it moved deeper into the void, the cold began to take hold. Without a star to warm it, the surface of this world plunged to temperatures that are difficult to comprehend. The thin atmosphere it might have possessed froze solid, falling to the surface as a blanket of exotic ice. Frozen nitrogen, frozen methane, perhaps even frozen oxygen. The planet became a dark, silent tomb, encased in a shell of perfect frost. Time, on such a world, loses all its familiar markers. There is no sunrise to mark the beginning of a day. There are no changing seasons to mark the passage of a year. There is only the continuous, unchanging dark. The surface of the planet is locked in perpetual midnight. The only light comes from the distant, smudged, glowing shapes of galaxies millions of light years away. They are so faint that they cast no shadows. If you were to stand on the surface of this frozen, wandering world, you would experience a silence so absolute it would feel heavy. There is no wind because the atmosphere lies frozen on the ground. There is no seismic rumble as the deep interior slowly settles into thermal equilibrium. There is only the quiet of stone and ice resting in the dark. For millions of years, the planet drifts. It moves at incredible speeds relative to its former home, perhaps hundreds of thousands of miles per hour. But in the vastness of the void, this speed is imperceptible. It seems to hang motionless in the deep. It is a lonely traveler, entirely disconnected from the grand, glowing structures of the cosmic web. It does not belong to a star system. It does not belong to a galaxy. It belongs only to the expanding void. And yet, despite the profound cold and the absolute isolation, this world is not completely dead. It is not at absolute zero. Deep beneath its miles-thick crust of frozen gases and ice, the core of the planet remembers the heat of its creation. The slow decay of radioactive elements and the residual warmth of the friction that formed the planet billions of years ago still generate a faint, deeply buried heat. This heat slowly, patiently works its way outward. It travels through the rocky mantle, through the layers of subsurface ice, until it reaches the frozen surface. It is not enough heat to melt the ice. It is not enough heat to power a weather system. It is only enough to raise the temperature of the surface just a few fractions of a degree above the ambient cold of the surrounding space. This microscopic difference in temperature is the source of the whisper. The frozen surface of the wandering world slowly radiates this internal warmth out into the intergalactic medium. It radiates it not as visible light, but as long, slow waves of thermal infrared energy. This energy spreads out in all directions, a faint sphere of warmth expanding into the freezing dark. As the waves of infrared light travel across the void, they encounter almost nothing. They move freely through the empty space, passing unimpeded through the sparse scattering of intergalactic atoms. They travel for millions of years. The universe continues to expand, and the space between the wandering planet and the distant Milky Way galaxy stretches, pulling the waves of light along with it, stretching them further, making them even longer, even fainter, even cooler. This is the signal. It is the last, dying breath of warmth from a banished world, echoing across an ocean of nothingness. And it is this incredibly faint, stretched, ancient breath of warmth that the James Webb Space Telescope, sitting quietly in the cold of our own solar system, managed to catch against the dark. To capture a signal so faint, the James Webb Space Telescope must perform a delicate dance with the laws of physics. Astronomy is fundamentally the study of light, and understanding how light behaves across the staggering distances of intergalactic space is crucial to deciphering the message it carries. When we talk about light, we are talking about a spectrum. Visible light, the colors of the rainbow that our eyes can perceive, is only a tiny fraction of this spectrum. The electromagnetic spectrum encompasses everything from the shortest, most energetic gamma rays to the longest, gentlest radio waves. The light we are concerned with, the light that carries the whisper from the void, lies in the infrared. Infrared light is the light of heat. Everything in the universe that has a temperature above absolute zero emits some form of light. You, sitting where you are glowing. You are emitting infrared light, which a thermal camera could easily see. A cup of warm tea emits infrared light. Even a block of ice emits infrared light, because even ice has a temperature above absolute zero. The rule is simple. The hotter an object is, the shorter the wavelength of light it emits. The incredibly hot surface of a young star emits short, energetic wavelengths, peaking in the ultraviolet and blue parts of the visible spectrum. A cooler star, like our Sun, peaks in the yellow and green. A still cooler object, like a glowing ember in a fire, emits mostly red and infrared light. Now, apply this rule to a rogue planet drifting in the intergalactic void. Its surface is unimaginably cold, perhaps only a few dozen degrees above absolute zero. Because it is so cold, the light it emits is incredibly weak, and its wavelength is very, very long. It sits deep in the mid to far infrared portion of the spectrum. This is the first challenge of detecting such an object. The light it naturally produces is invisible to human eyes and to most traditional telescopes, which are designed to capture visible or near-infrared light. The second challenge is the distance. The universe is governed by the inverse square law of light. Imagine a candle burning in the center of a dark room. If you stand 1 foot away, the candle appears bright. If you step back to 2 feet away, the light from the candle has to spread out over a much larger area to reach you. In fact, it spreads out over 4 times the area. So, at twice the distance, the candle appears only 1/4 as bright. Now imagine that the candle is a faintly glowing frozen planet, and you are stepping back not 2 feet but millions of light years. The tiny amount of thermal infrared light emitted by the rogue planet spreads outward in a vast, expanding sphere. By the time that sphere reaches our solar system, the light is incredibly diffuse. The photons. The individual packets of light energy are spaced very far apart. To catch enough of these widely spaced photons to build a recognizable signal, you need a very large bucket. This is why the primary mirror of the James Webb Space Telescope is so massive. At 21 feet across, its golden surface acts like a giant funnel, collecting and concentrating the sparse rain of infrared photons falling from the deep sky. The third challenge is the stretching of space itself. As we established, the universe is expanding. The space between the rogue planet and the telescope is continuously growing. Think of a wave of light as a slinky stretched out between 2 people. If the 2 people slowly walk away from each other, the coils of the slinky are pulled further apart. The distance between each peak of the wave increases. When the rogue planet emitted its faint infrared glow, the light had a specific wavelength dictated by the planet's temperature. But as that light traveled across the expanding intergalactic void, the space it was traveling through stretched. The waves of infrared light were pulled out, becoming longer and longer. This cosmological redshift means that the light arriving at the telescope is even longer in wavelength and even lower in energy than the light that left the planet. The telescope must be tuned to look for the light not as it was when it was created, but as it is now, after its long, exhausting journey across the stretching cosmos. The final, and perhaps most difficult challenge, is the noise. Space is dark, but it is not perfectly black. Our solar system is filled with a thin cloud of dust, leftover debris from the formation of the planets and the crumbling of comets. When the sun's light hits this dust, it warms it up. This warm dust glows softly in the infrared. This phenomenon is called zodiacal light. To the James Webb Space Telescope, this local glowing dust is a bright fog. Trying to see the faint thermal signature of an intergalactic rogue planet through this fog is like trying to see the glow of a firefly across a valley while looking through a dirty window illuminated by a street lamp. And the noise does not end there. Beyond our solar system, our own Milky Way galaxy is filled with vast, sweeping clouds of gas and dust called galactic cirrus. These clouds also glow in the infrared, warmed by the collective starlight of billions of neighboring suns. To find the true signal from the void, astronomers must engage in a process of meticulous mathematical subtraction. They take the raw image from the telescope, which is flooded with the infrared light of our own solar system and our own galaxy. They use complex computer models to carefully map out the exact brightness and shape of the zodiacal dust and the galactic cirrus. Then, layer by layer, pixel by pixel, they subtract that local noise from the image. It is an exercise in extreme patience and precision. They peel away the light of our neighborhood. They peel away the light of our galaxy. They peel away the light of the countless background galaxies that dot the distant universe. When all the noise has been mathematically stripped away, they are left with the deep background. They look at the remaining data, searching for the slightest anomaly, the faintest peak in the spectrum that cannot be explained by anything else. And there, in the quieted data, the signal remains. A gentle, persistent curve in the infrared spectrum. A shape that perfectly matches the mathematical prediction for a small, solitary body cooling endlessly in the dark. This gentle science, this soft uncovering of truth through the careful gathering of invisible light and the patient subtraction of noise, allows us to reach out and touch the untouchable. We cannot travel to the intergalactic void. We cannot send a probe to orbit this lonely, wandering world. We can only stand on the shores of our own cosmic island, build golden mirrors to catch the faintest ripples of the cosmic ocean, and listen carefully to the silent stories written in the stretching light. When the noise of our local solar system and our bustling galaxy is finally stripped away, and the pure, faint signal from the intergalactic void remains, we are left to contemplate the physical reality of the object that sent it. The mathematics and the spectral lines point toward a rogue planet a solitary wanderer in the deep dark. But to truly understand such a world, we must set aside our earthly biases of what a planet should be. Our world is defined by its relationship with the sun. The sun dictates our temperatures, drives our weather patterns, fuels our biology, and measures out our days and our years. A world without a star is a world that has been unmoored from the very concept of time as we experience it. Imagine the slow, inevitable transformation of a planet that has been cast out of its solar system. As it travels further and further from the warmth of its parent star, the great cooling begins. It is not a sudden freeze, but a gradual, majestic settling into a new state of being. First, the weather systems would slow down. The mighty storms, driven by the unequal heating of the sun on a rotating sphere, would lose their energy. The winds would die down, becoming gentle breezes, and then stilling completely. The atmosphere, once a dynamic envelope of circulating gases, would grow heavy and quiet. As the temperature drops, the gases in the atmosphere would begin to condense. If the planet possessed water, the oceans would have frozen over long before, forming a thick, planet-wide crust of ice. But in the deepening cold of the void, even the air itself begins to freeze. Carbon dioxide would fall as a dry, powdery snow, dusting the ice sheets. Then, as the temperature plunges further, toward 200 degrees below zero, nitrogen and oxygen would liquefy, raining down to form shallow, freezing lakes before finally freezing solid themselves. Eventually, the planet is left with no atmosphere at all. It is encased in a multi-layered shell of exotic ices. It becomes a perfect mirror, reflecting nothing because there is no light to reflect. It enters a state of deep, enduring hibernation. In this frozen state, an intergalactic rogue planet is incredibly stable. A planet orbiting a star is subjected to constant change. It is bombarded by solar radiation. Its atmosphere is slowly stripped away by stellar winds, and it faces the eventual destruction that comes when its star reaches the end of its life, swelling into a red giant and engulfing the inner worlds. But a rogue planet in the void has escaped all of this. It has reached the ultimate safe harbor. There are no solar flares to scorch its surface. There are no nearby stars to go supernova and bathe it in deadly radiation. There are no other planets to perturb its path. It is alone, and because it is alone, it will endure almost indefinitely. It will outlive the star that birthed it. It will outlive the galaxy that expelled it. It will drift through the expanding universe for trillions of years, virtually unchanged. Yet, unchanged does not mean dead. The surface of the world is a frozen tomb, but the interior tells a different story. Planets are formed in the violent, energetic collisions of dust and rock in the early days of a solar system. This process of accretion generates an immense amount of heat, melting the young planet into a glowing sphere of magma. Over millions of years, the heavier elements like iron and nickel sink to the center to form a dense core, while the lighter rock floats to the surface to form a mantle and a crust. Even after the planet is cast out into the freezing void, that primordial heat remains trapped inside, insulated by thousands of miles of solid rock and ice. Furthermore, the rocky core contains trace amounts of radioactive elements, such as uranium and thorium. As these elements slowly decay over billions of years, they release a steady, quiet warmth. This internal heat source changes the nature of the rogue planet entirely. If the planet is large enough, and if it contains a significant amount of water beneath its outer layers of frozen gases, this geothermal heat can create something truly miraculous in the absolute dark, a subsurface ocean of liquid water. Beneath a crust of ice that might be 10 or 20 miles thick, a global ocean could exist, kept warm by the slow, steady heartbeat of the planet's core. The water at the very bottom of this ocean would be in contact with the rocky mantle. Here, geothermal vents, similar to the hydrothermal vents found in the deepest, darkest trenches of Earth's oceans, could release heat and mineral-rich fluids directly into the water. In the crushing pressure and absolute blackness of this hidden ocean, the conditions for chemistry, and perhaps even for biology, might quietly persist. It would be an ecosystem completely independent of starlight. If life were to arise, or if it had already arisen before the planet was ejected from its star system, it could survive here in a state of slow, steady equilibrium. It would be a quiet life. Without the abundant energy of a sun, organisms would likely operate at a much slower pace. The rhythm of existence would be measured not by days or seasons, but by the slow convection of warm water rising from the dark sea floor and the gentle shifting of the ice above. We do not know if such subsurface oceans exist on the intergalactic wanderer detected by the James Webb Space Telescope. We cannot peer beneath the ice, but the simple, undeniable fact that the planet is emitting a signal, that it is radiating a faint signature of heat into the void, tells us that its core is still warm. It tells us that the engine of the planet is still running, however quietly. When we consider the vastness of the intergalactic medium, the sheer volume of space that exists between the glowing islands of the galaxies, a profound thought emerges. The ejection of planets is a natural, common consequence of galactic dynamics. Trillions of stars interacting over billions of years must have cast out an innumerable host of worlds. It is entirely possible that there are more rogue planets wandering the dark spaces of the universe than there are stars shining within the galaxies. The luminous, structured cosmos that we can see might be only a small fraction of the whole. The spaces we thought were empty might in fact be filled with a silent, unseen population of nomadic worlds, carrying their internal warmth and their hidden oceans through the endless night. These wandering planets are the quiet majority of the cosmos. They do not announce their presence with brilliant flares of fusion. They do not gather in grand, swirling spirals to paint the sky with light. They simply exist, steady and enduring, drifting at the gentle pace of the expanding void. They are the deeply buried stones in the cosmic garden, holding on to their quiet histories, waiting for an eye sensitive enough to perceive their subtle glow. To find one of these hidden stones, to catch the faint, stretched signal of a solitary world wandering between the galaxies, is a triumph of human patience and ingenuity. It brings us full circle, back to the golden mirrors floating 1,000,000 miles from Earth. The James Webb Space Telescope was not built solely to find rogue planets in the dark. It was built to look back in time, to see the very first stars and galaxies igniting in the dawn of the universe. It was built to peer through the thick dust clouds of stellar nurseries, to watch the chaotic birth of new worlds. It was designed to answer the grandest questions about our cosmic origins. But a telescope of such profound sensitivity cannot help but reveal the quiet truths of the present, alongside the loud echoes of the past. By opening its eye to the infrared universe, Webb has shown us that the cosmos is a place of infinite nuance. The title of our exploration, that James Webb detected a signal from intergalactic space, sounds, at first, like the premise of a science fiction story. It evokes images of messages sent across the void, of grand discoveries that upend our understanding of reality in a single, dramatic moment. But the reality of the signal is far more beautiful and far more comforting than any dramatic fiction. The signal is not a shout for attention. It is the simple, undeniable evidence of existence. It is the physical universe, following its quiet laws of thermodynamics, whispering that nothing is ever truly lost. A planet, violently ejected from its home, cast into an ocean of profound emptiness, stripped of its star and its sky, does not cease to be. It carries its history within its core. It holds onto the heat of its creation, and it slowly, patiently breathes that warmth out into the dark. For millions of years, that breath of thermal radiation traveled outward. It crossed a distance so vast that the very space it moved through expanded, stretching the light, softening it, turning it into the longest, faintest waves of infrared energy. It was a light that was destined to be ignored. The universe is filled with brighter things. The glowing gas of nebulae, the furious accretion disks of black holes, the collective brilliance of 1,000,000,000,000 suns. These are the things that command the attention of the cosmos. The faint warmth of a single frozen rock is a whisper in a hurricane. And yet, we built a machine capable of hearing the whisper. We gathered the lightweight metal of beryllium, forged it into hexagonal panels, and coated it in a microscopically thin layer of gold. We packed it into the nose cone of a rocket, launched it through the turbulent atmosphere of our own world, and sent it out to the quiet cold of Lagrange Point 2. We unfurled a shield the size of a tennis court to block out our own sun, ensuring that the golden mirrors would be bathed in absolute shadow, cooled to temperatures that mimic the deepest voids. We did all of this because we possess a fundamental need to know what is out there. We are driven by a quiet, persistent curiosity that is not satisfied by looking only at the brightest objects in the room. We want to know the shadows. We want to understand the spaces in between. When the scientists directed the telescope toward that dark, empty patch of the sky, they were practicing a form of cosmic meditation. They were choosing to ignore the obvious, to look past the glowing filaments of the cosmic web, and to focus on the spaces where nothing seemed to be happening. And the universe rewarded that patience. The long, stretched photons, exhausted from their journey across the expanding void, finally found a resting place against the gold. The signal formed. A faint, steady curve on a graph, telling the story of a lonely traveler in the dark. This detection changes how we feel when we look up at the night sky. We will still see the bright twinkling stars, and we will still marvel at the faint glow of the Milky Way. But we can now look at the dark patches between the stars with a new understanding. We know now that those dark spaces are not empty. The void is not a barren wasteland. It is an ocean, vast and quiet, and it is populated by countless wandering worlds. They are out there right now, drifting in the eternal midnight encased in ice, keeping their inner fires warm. We will likely never visit them. The distances are simply too great, the travel time too immense for our brief human lives. But we do not need to visit them to know they are there. We do not need to touch the ice to feel the reality of their existence. It is enough to know that we have built an eye capable of seeing their faint, persistent glow. It is enough to know that in a universe defined by unimaginable distances and overwhelming darkness, even the smallest, most isolated objects can still reach out and touch a golden mirror. The James Webb Space Telescope will continue its silent vigil. It will continue to orbit in the deep freeze, gathering the ancient light of the first galaxies and mapping the atmospheres of distant worlds. And occasionally, as it stares into the deep, quiet voids, it will catch another whisper. It will map another invisible stone in the cosmic garden. The universe is a vast, echoing space, but it is deeply connected by the slow, patient travel of light. We are part of that connection. By listening to the dark, by tuning our instruments to the faintest frequencies of existence, we find a profound sense of peace. The cosmos is not just a place of bright, violent energy, it is also a place of enduring quiet, holding its secrets safely in the cold, waiting for a listener patient enough to hear the signal from the void. To truly appreciate the nature of this faint signal, we must expand our understanding of time. Here on Earth, our lives are dictated by the rapid, rhythmic ticking of the planetary clock. We measure our existence in days, seasons, and years, brief cycles tied to our orbit around a warm, turbulent star. Even the history of our species, stretching back a few 100,000 years, is nothing but a fleeting spark in the grand scale of the cosmos. When we look at the stars, we are looking at objects that operate on a different temporal plane. A star like our Sun will burn for roughly 10 billion years. This seems like an eternity to the human mind, but in the life of the universe, it is merely a single phase. Stars are born, they burn through their nuclear fuel in a frantic struggle against the crushing force of their own gravity, and eventually, they die. They cast their outer layers into space, or they detonate in brilliant supernovae, leaving behind cooling embers, white dwarfs, neutron stars, or black holes. The galaxies, those great cities of light, are also subject to the ravages of time. They consume their available gas, forming fewer and fewer new stars as the eons pass. They collide, distorting their elegant spiral arms into chaotic shapes, eventually settling into massive, diffuse elliptical clouds of aging red stars. The era we live in now, known as the Stelliferous era, is a time of abundant starlight and energetic cosmic events, but it will not last forever. Eventually, trillions of years from now, the last stars will exhaust their fuel and fade into darkness. The galaxies will dim. The universe will enter the degenerate era, a time when the only objects remaining are the stellar corpses and the quiet, unseen masses that have always inhabited the shadows. This is where the rogue planets, those wandering worlds cast into the intergalactic void, reveal their true significance. A planet without a star is an object perfectly adapted for the deep future. It has already experienced the death of its sky. It has already settled into the profound cold. While the glowing stars burn themselves out in a spectacular display of energy consumption, the solitary rogue planet simply endures. It is a master of conservation. The thick crust of exotic ices that encases such a world acts as the perfect insulator, trapping the faint radiogenic heat of the rocky core deep inside. A star loses its heat rapidly, pouring it out into the universe. A frozen, wandering planet hoards its warmth, releasing it so slowly that the core could remain active for trillions upon trillions of years. When the James Webb Space Telescope detected the faint, stretched infrared signal from the intergalactic space, it was not merely looking at a distant object. It was, in a profound sense, looking at a survivor. It was gathering the slow, patient breath of a world that is already living in the conditions of the far future universe. As we track the expansion of the cosmos, we know that the voids are growing. The mysterious force we call dark energy is stretching the fabric of space-time, pushing the great filaments of the cosmic web further apart. The spaces between the galaxies are becoming wider, deeper, and even more isolated. For a rogue planet drifting in this expanding emptiness, the rest of the universe is slowly receding. The distant, smudged galaxies that once offered a faint glow in the sky are becoming dimmer, their light stretched into invisibility by the accelerating expansion. Trillions of years from now, a wanderer in the deep void will be entirely alone. No light from any other object will ever reach it. It will sit in the center of an unobservable universe, holding on to its final internal embers of heat. Knowing this changes the way we interpret the signal Webb found. It is not a sad or melancholic discovery. It is a testament to the incredible resilience of matter. The universe is heavily biased toward destruction and decay. Entropy, the steady slide from order into chaos, is the ultimate law of nature. Yet here is an object that has found a way to resist the rush of time. By retreating into the dark, by freezing its surface and silencing its weather, it has achieved a state of near-perfect preservation. The infrared light that struck the golden mirrors of the telescope traveled for millions of years to tell us this story. It is a story of quiet endurance. It reminds us that existence does not require a center stage. A world can be complete, complex, and enduring, even if it never again feels the warmth of a sunrise. Let us consider the physical reality of this unseen world, building a picture in our minds using the precise language of chemistry and thermodynamics. The signal detected by the James Webb Space Telescope gives us a thermal profile, a subtle hint at the temperature and the mass of the object. From this, the laws of physics allow us to deduce what kind of materials might make up this lonely traveler. If this rogue planet was ejected from a planetary system similar to ours, it carries the same basic ingredients that formed the Earth, Jupiter, and Neptune. But in the near absolute zero of intergalactic space, these familiar ingredients take on alien forms. We can imagine the surface as a vast, smooth plain of frozen gases. In our solar system, nitrogen makes up the bulk of the air we breathe. On a world drifting between the galaxies, the nitrogen has long since fallen from the sky, forming vast, slow-moving glaciers. These glaciers do not carve through rock like the ice rivers of Earth. They are rigid, brittle, and perfectly still, locked in the deep freeze. Methane, a gas on Earth, would form solid, dark plains, perhaps cracked by the slow, microscopic shrinking of the planet as it loses its internal heat over billions of years. If the planet possessed water, it lies far below this exotic surface, crushed into strange, high-pressure phases of ice that do not exist naturally on our world. Ice that is denser than rock, completely solid, and utterly black. Yet, as we move deeper into the planet's interior, the story changes. The crushing weight of the miles of ice and frozen gas above creates immense pressure. And at the very heart of the world, the rocky core continues its slow, patient work. The radioactive isotopes of uranium, thorium, and potassium, incorporated into the rock when the planet first formed from a swirling nebula, continue to decay. This decay releases energy. It is a very small amount of energy, a gentle trickle of warmth compared to the raging nuclear fusion of a star. But insulated by the massive layers of ice, this heat accumulates. It warms the rock, and the rock warms the layer of ice directly above it. If the balance is exactly right, if the planet is massive enough to have a large core, and if the insulating ice is thick enough, this deep hidden boundary can reach the melting point of water. This is the great secret that a rogue planet might hide from the cold universe. A global ocean, entirely sealed off from the vacuum of space, existing in perpetual, crushing darkness. The water in this ocean would be rich in minerals dissolved from the warm rock below. It would circulate slowly, driven by the faint thermal currents rising from the core. It is entirely possible that the faint infrared signal gathered by the James Webb Space Telescope is the heavily muffled signature of this internal warmth. The heat from the core travels slowly outward through the liquid ocean, then conducts its way out through the miles of solid ice, until it finally reaches the frozen surface of the nitrogen glaciers. By the time it reaches the vacuum of space, it is nothing more than a whisper of thermal radiation, a fraction of a degree of warmth against the absolute zero of the void. This delicate transfer of energy is what the telescope detected. It is a profound realization that we, sitting safely in the warm, illuminated neighborhood of our sun, have developed the technology to feel the heat radiating from the frozen crust of an invisible world millions of light years away. The data from the telescope arrives on Earth as a sequence of numbers, a digital stream capturing the impacts of individual, long-wavelength photons. It takes weeks of careful processing by dedicated astronomers to translate these numbers back into the physical reality of the universe. They must mathematically peel away the bright infrared glow of our own solar system's dust and carefully subtract the scattered light of distant galaxies to isolate the single distinct emission from the wandering planet. This process of looking and listening requires a state of calm focus. It is the antithesis of the loud, fast-paced world we often inhabit. Astronomy of this caliber is a slow science. It asks us to be patient, to stare into the dark patches of the sky, and to trust that the universe will slowly reveal its quietest inhabitants. The signal from intergalactic space is a gentle reminder of our own capacity for connection. We are made of the same heavy elements that make up the rocky core of that distant world. The iron in our blood, the calcium in our bones was forged in the same ancient generations of stars that birthed the rogue planet. We share a common origin in the dusty nebulae of the past. Though we are separated by an ocean of empty space so vast it defies comprehension, we are connected by the simple, enduring laws of physics. We emit heat into our local environment, and the wandering world emits its faint heat into the void. Through the golden mirrors of the James Webb Space Telescope, we have reached across that immense distance and felt that warmth. The universe is a place of profound scale and overwhelming silence. But it is not a lonely place, so long as there are eyes willing to look into the dark and minds willing to understand the quiet, enduring signals drifting through the spaces in between.